Today, we're exploring the Boids simulation, a computational model used to simulate the flocking behavior of birds. In my opinion, this is one of the most elegant examples in computer science of how complex behavior can emerge from a few simple rules. Created by Craig Reynolds in the 80s, he used the name Boid as just a shortened version of birdoid object. Let's start with a few Boids moving around randomly. The only thing I've done is applied a force to those that go out of bounds to bring them back in, which I'll show with this white rectangle. Just like in real life, birds can't see the entire flock, so we give them a visual range that determines how far they can see. At its core, each Boid only follows 3 rules. The first rule tells it to avoid getting too close to its neighbors. Just like how in real life, birds don't crash into each other. If 2 Boids get too close, then we apply a force to separate them. We weight these vectors inversely by distance, so that the closer 2 Boids are, the stronger the force pushing them apart is. The arrow here shows the direction of the separation vector, which pushes our red Boid away from any others that get too close. Something to note here is that when calculating the separation force, we give each Boid an additional protected range, which is smaller than its visual range. Boids only move away from each other if they are in each other's protected range. This mimics how in reality, birds want to be close to each other, but not too close. The second rule is alignment, which just means that each Boid tries to match the average direction of its neighbors. The arrow here points in the average direction of all Boids within the visual radius. Now this is starting to look a bit more bird-like. The third rule is called cohesion. Boids don't like being alone, so they steer towards the average position of their neighbors. Arrows here point towards the average position of other Boids within the visual radius. You can see that if I increase cohesion to a really large value, the Boids clump together and slow down a lot. But I found that a value of about 0.2 looks pretty good. That's it. No central coordination, no complex communication. Just these 3 local rules applied by each individual Boid gets us some really intriguing results. It's also a lot of fun tweaking random things in the simulation, like setting each Boid's color based on the density of Boids at that position. I also like varying the values of each rule, like setting the separation really low so that they all clump together, then suddenly making them shoot out. There's a lot more we can do here. For one, at the moment it's not very efficient, because to calculate the force on each Boid, we loop through all other Boids, which is an O of n squared operation. Using something like a spatial partitioning grid would really help to speed this up. We could also experiment with adding obstacles or predators, but in this video I just wanted to provide an overview of how the simulation works, so I'll leave it here for now. Thanks for watching.